Alright, so the triangle law of vector addition says that if you connect the head of one vector to the tail of the other, then the resultant is given by the tail of that first vector connected to the head of the other vector. So let's put that in a graphical form. So say you have a vector A in blue, right? And you have another vector which we shall draw in red, is the vector B, right? So we've placed the vector A's arrowhead at the tail of the vector B. So the resultant of this vector A and B, which is A plus B, is actually this vector which goes from the tail of A to the arrowhead of B, right? So C is equal to A plus B, where C is called the resultant. C is the resultant vector, right? Resultant vector. Similarly, we have the parallelogram law, right? So, parallelogram law. What we have here is we have a vector B, and we'll take the vector A again in blue, right? And these may be the same as the previous ones or whatever, it doesn't matter. Oh, oops, that should be B. These could be the same as the previous vectors, or it could be absolutely new vectors. But what you do is you place them tail to tail, then you construct these imaginary dotted lines, right? So you go like that. So now you've constructed a parallelogram. The parallelogram law says that the effect of adding vectors A and B when they're placed in this fashion is a vector C, which is the diagonal of the parallelogram. So this is the vector C, right? And you can actually see that if this vector B on this side, right, is projected onto the vector or this extension on this side, on the right side, it's actually the same thing as the triangle law, right? So you have the vector A over here and the vector B going along this line. So you get the parallelogram, the triangle law back. So you can see that the effect of either using the parallelogram law and the triangle law are equivalent. So these are the two rules of vector addition, right, or two methods of performing vector addition. There are some properties associated with vector addition, so let's get them. Let's take a look at them. So vector addition properties, right? Addition properties. Vector addition is commutative, so that's a star. I'm saying this is commutative, which means that A plus B is equal to B plus A. A plus B is the same as B plus A. So the order of addition does not matter. You could take the vector A and add it to the vector B, or you could take the vector B and add it to the vector A. You could also, by looking at the triangle law, say that you could take the arrowhead of the vector B, right, and place it at the tail of the vector A, and then construct the same resultant vector as we've done in the previous case. You would still reach the same result. So it does not matter what the order of the operation is, right? And yeah, you will see that this kind of commutativity does not hold in certain cases of multiplication of vectors when you do the cross multiplication, and but it might hold. It does hold in the case of the dot products. So this is one property of vector addition. Another property of vector addition is that it is associative, right? Associative, which means that if you have, say, three vectors P, Q, and R, it does not matter in what order you add them. So you could take the vectors p plus q, add it to r. That would be the same as taking the vectors, again, we'll write them as p, q, and r, and the brackets over here, or the parentheses, just denote the order in which the operations are being performed. So in the first expression to our left over here, I'm saying that you add the vectors p and q, and then the resultant of p and q is added to r. The result that you get, that total vector from this entire operation on the left, is the same as the operation on the right, where q and r are added first, and then added to the effect of the vector p. Alright, so with this we complete vector addition, and we will now move to multiplication.